Here we want to use the exponential growth equation to examine a situation in which the interest, the APY, annual percentage yield, that's the interest on a particular investment, is 6%. Okay, in that investment, we have an initial amount of $1,500, and it's asking how much is in the account after 10 years. Okay, well, we've seen these kinds of interest problems before, I would imagine. Somewhere in your mathematical career, you've done something like this, and you probably used what I'll call the old equation. A equals P times the quantity 1 plus R over N to the NT. So hopefully that equation is mildly familiar to you, but even if it's not, it doesn't matter because we're not going to use it. But just kind of as a throwback here, if you remember how this went, this is annual percentage yield, so N was 1, so we really have principal times 1 plus R to the T. And the principal was the initial amount, so that gives us, okay, the new amount is the principal, so 1,500. 1 plus R, 0.06. Remember, the rate always goes in as a decimal, so 1.06 to the, well, N is 1 again, so we just have T. And that happens to be to the power of 10 in this case. So let's just compute it out. We have 1,500, 1.06 to the 10. It comes to about $2,686.27. Okay. But that's the old way of doing it, which is perfectly fine, but the idea here is we want to look at all of these exponential growth situations with the same equation to show the universality of this y equals y naught e to the kt. And when you have money in an account accruing interest like this, it turns out that that's exponential growth as well. So we should be able to use this new equation and model it that way. So instead of A being the amount, let's let Y be the amount. And instead of the principal being the initial amount, let's let Y naught be that initial amount. So we then have Y equals Y naught, and then we're at 1.06 to the T. So I just borrowed from our older equation here and just put in some new variables. So we're getting closer, but we still want this E in here. So I'll use a trick, and in doing this we'll discover a shortcut so we don't have to go through this reasoning each time. Here's the trick. Anytime you have some base to an exponential b to the x, you can write that base, so I'm just going to leave the x hanging out here. I'm going to write that base as e to the natural log of the base, because the e and natural log are inverse functions of each other, and those will undo each other, and that would just leave b to the x again. And then we write this as e to the natural log b times x. So for our example, this becomes y equals y naught stays the same, e to the natural log 1.06 all times t. Times t. And there's the equation that we'll work with. So we don't want to have to go through all this reasoning every time. But we can see from this that there's a direct way to go straight to our growth and decay constants, k. Anytime we have growth, our constant k is going to be natural log 1 plus r, where r is the rate in decimal form. And anytime we have decay, k is going to be natural log of the quantity 1 minus r, where r is again in decimal form. With these two versions of k, we can go straight to the exponential version of the equation without needing to reason our way to it each time. Okay, so let's finish out this example using the e version of the formula. So we have y, which will be our new amount, equals y naught. Well, that was 1,500. Okay, e to the natural log 1.06, and then we're looking at 10 years. So in your calculator, you need to make sure that somehow these things stay in the exponent. So every calculator is different, but you may need to put parentheses around these in the exponent. Otherwise, that 10 tends to come down. You're multiplying by 10 down here, which you don't want. Okay, well, computing this out with a calculator, again, gives the same thing, of course. $2,686 and about 27 cents. So you may be asking, what was wrong with the old way? Why not just keep using that? Well, this new approach can be used for all exponential growth. So it's useful to see how all these things are actually the same mathematically. All these different situations where things are growing exponentially stem from the same equation. That's the usefulness of approaching it this way.